All right, so we'll go ahead and get started now. For those of you that do not know me, my name is Kevin Sigwart. I am the Director of Solutions at One Spatial Inc. And just to do some logistics, I think the way that we're going to organize this, we have a lot of people that are signed up for this webinar. So what we'll do is I'll spend about 50 minutes going over the presentation, and then the last 10 minutes we'll open it up for questions. But what we'll do is we'll just use the questions inside the GoToMeeting interface or GoToWebinar interface. So if you have any questions throughout the presentation, feel free to enter them in. We will try to answer some of them while we're doing the presentation, but most likely we'll get to most of them at the end of the presentation. And so with that, and I have also on the line, and he's muted right now, but is Des Grain, and he's the one that's going to be probably asking the questions at the end. So he's going to be following the questions coming in the screen and address them as they come up. So today we are going to be talking about how we can leverage technology and tools to enforce data governance in transportation. Data governance is a pretty hot topic in transportation. I was at TRB back in January, and I'm pretty sure data governance came up in nearly every single presentation. So there is a lot of interest in data governance. And I think one of the main reasons why there's so much interest in these days in data governance is that we are starting to collect data from so many different sources, and the amount of data is becoming extremely difficult to manage. So without having proper policy and organizational structure for the way that you manage your data, it's going to become unmanageable. So, and to continue that point is that recently IBM did a study, and they found that the poor data quality is costing the U.S. economy $3.1 trillion a year. And a lot of this is being caused from the amount of time waste. And I'm sure all of you on the line that have worked with data as analysts have done something similar. And I know I have. You collect data, you need to solve some sort of problem. So I go into my database and I collect whatever data sources I need. I realize that the data doesn't exactly fit quite right. So then I manually go in and massage the data to get it ready, to get it fit for purpose. And then once I get it all fit for purpose, then I try to do my analysis against it. I get my result. I store all of that data that I was doing the massaging on my local machine and never gets pushed back to the source database. And then my coworker does the exact same thing 2 weeks later. And this just keeps on occurring and occurring. There's no feedback loop. So there's so much time waste and users going through and manually doing that validating and correcting the data themselves. So being able to provide some sort of feedback can really save a lot of organizations waste and money. There's also lots of loss of revenue and resources wasted making decisions on bad data. I know what's interesting also about this study is that they also found that 1 in 3 executives did not have confidence in their source data sets. So if you don't have, if you're either you're making decisions on data that you're not confident in, that's troubling enough because you're going to make bad decisions. But if you're not confident in the data, you're probably not going to trust the results you're getting. So then you're going to start making decisions on your gut instinct as versus what the data is telling you to do. So these things need to be addressed. And this is where data governance can come into place. And then lastly, worst case scenario is that lives are being put at risk because you're making these decisions on poor data quality. So the way that we can address this is the cost of poor data quality is coming up with proper data governance. And data governance there's a lot of different aspects to data governance. There's the way that you are architecting your data. How do you facilitate who's responsible to edit what data? How does that data feed from different systems? How do you secure that information? Where do you store that information? All sorts of different aspects. What we're going to focus on today is on the quality control aspects, the metadata and interoperability. And when we're looking at our data systems, we have a variety of different systems, and they're typically siloed off. And this is not a surprise. A lot of times, there's these departments get siloed off because of the way that we structurally organize our companies. We have a GIS department, we have a sales department, we have a project management department. All of these organizations are operating fairly independently, so it creates these silos. But not only that, is that these organizations are also using their own systems. So in the GIS group, they're probably using some sort of GIS technology that is the best in breed technology for doing geospatial analytics. If you think of like a sales organization or a sales department, they may be using something like Salesforce to manage their data. Nobody's expecting the sales group to be managing their data inside of a GIS, and nobody inside of a GIS can expect to be doing GIS in Salesforce, right? So it creates these silos, but unfortunately, we need to be able to share data across these different organizations, and we have to trust the data that we're sharing is actually fit for purpose and of good quality. And when we actually look at the way that these different systems are actually architected or actually work, there's a lot of overlap. So there's places where we are bringing GIS data into our project management systems, and there's places where our asset management systems are overlapping with GIS, or where CAD is overlapping with GIS. So all these different points of where we're having these overlaps need to be addressed. How do we facilitate the data going from one system to another system? Who's responsible for editing that data? How do we ensure that the data, before it goes into the existing system, it's actually fit for purpose? And that's where we get into coming up with some sort of data governance plan to determine who's responsible for editing what does it mean to have quality data, and then what we're going to do with it from there. And at One Spatial, where we really focus in on is on what we call location master data management. And this is facilitating your data governance plans. So you have your source data, and where we want to get our clients is we want to be able to have them be able to make actionable, knowledge, data-driven answers to using that data. And how we get there is we want to leverage a rules-based approach. So if we look at the bottom of our data curve here, we can see that the data does have some value. But if you're not confident in the data itself, you don't feel that it is of good quality, you're not going to trust the decisions that you're going to try to make off of that data. So the first thing you have to do to provide value to that data is to make sure that data is fit for purpose. And at One Spatial, we have a validation engine called One Integrate that does the data validation and data cleansing of the data. You take your business rules, where if you define those business rules in your data governance plan, you could take those business rules, integrate those inside the One Integrate product so that you write the validation rules against the data sources. And then it can pinpoint locations of where there's potential issues with your data and drive the user to those locations. You can also do the data cleansing. So if you identify issues with the data sets, you could tell the system how to auto clean those data sources. So you can either drive users to clean the data, or you can automate the cleaning of the data. So once you start getting more confidence in your data sources, you then can start to integrate it with other sources of data so that you can bring in other data sources. So what we can also do with the One Integrate technology is we can connect to a variety of different sources of data. So we're not limited to one type of data source. We're really data agnostic. So we could connect to geospatial data. We could connect to non-spatial data. So maybe you have a GIS database that has your route information and has a series of measure values associated with those routes. But then you have some sort of an LRS-based system, a linear reference system, that is based off of where the begin and the end measure values are along of our particular route. So how do you integrate these two different data sources? Well, we could bring them in, and then we could start to write validation rules across those two different data sources. But then we can also create products from integrating those two different data sources. And this can also work with multiple different geospatial data sets for doing spatial alignment or bringing in things like CAD drawings. Once we start doing all this integration, we now have actual information that we're building from those data sources. And with that information, we could start to do more advanced analytics. So some of the work that we've done on data inference is where when we're bringing these data sources together, we can start to infer where missing assets may exist. And we've done this work for pipeline data specifically, where we've inferred where pipelines should exist by bringing in information from CRM systems, the GIS systems, and so forth. So being able to bring all this information, and we can start to infer where we're missing assets and build those assets to spec. So now we're getting knowledge and insight. And the last thing we want to be able to do is we want to be able to have this actionable information. So what we can do is we partner with different organizations. So for example, we're business partners with Esri, Safe Software, Latitude Geographic, and Oracle, and among others. And we build end-to-end solutions so that we could take your data, make sure it's fit for purpose, make sure it's integrated, providing good knowledge and insight, and then providing that workflow so that you can drive the users to making sure that they have an adequate solution. And we've been doing this for a variety of different years. So over the past 45 years, we started 45 years ago in Cambridge Labs in the UK. And we have been developing data management solutions ever since then. About 7 years ago, we started up in the US, and where we started the One Spatial Inc., which is a fully owned subsidiary of One Spatial Group operating in the US. And we have been working with a variety of different clients from the federal all the way down to the local government. In transportation specifically, we've been doing work at the Federal Highways Administration, where we have revamped their HPMS validation rules to run them inside of our One Integrate product. So we can run the HPMS validation rules now inside that product. Now, what the idea is that they are going to be implementing HPMS 9.0, and as part of that, they're going to be leveraging the One Integrate technology as part of that implementation. And there's going to be some changes to the way that they do the HPMS validations as part of this. They're going to be, instead of doing just attribution level checks, they're going to start doing spatial checks along with that. And I have a demonstration showing you some of that we will highlight in about 15, 20 minutes. We've also done work at other state level DOTs. So at Kansas DOT, we have helped them clean their data up to get it ready to go into roads and highways. So they had this data set that they needed to get cleaned up. They were expecting it was going to take them about a year to get cleaned up, but they only had about 3 months to get it cleaned and get it submitted to federal highways for the HPMS submission. So we were able to facilitate validating the data and automating the cleanup of the data to get them so that within a month they had the data already fit for purpose. So really trying to get them quicker to the end game that they need to get to. And then we've also done work at the county level. A lot of this has been more in the next gen 911 arena. So it's sort of transportation, but I'm pretty sure most of the people on this call are not in that arena. So on the next side of things is that not only are we doing automated quality control, validation, and cleanup, we've also done work with change detection and conflation, so integrating data sources. One of the good examples of this is the work that we did at the US Census. So for the US Census, we provided a workflow to help them deal with the roll-up effort of their Tiger Centerline program. So they are collecting data from 3,200 different data providers that they're trying to ingest into their Tiger Road Centerline data set. So as part of that, they are leveraging our technology, or the One Spatial technology, to validate the data, to make sure that the data that's coming in from these data providers are fit to the business needs of the US Census. They then do a schema mapping exercise to get the data from the source data set to get it to a consistent schema. They then use the rules to do the change detection to determine what's different between what the data provider is providing and what the source data set is. And then once they do that change detection, they then spit out a bunch of proposals with a confidence level score based off of all those different proposals. Those proposals get fed into a workflow where they are, if they are meeting a certain threshold, they go to the, they immediately get ingested into the system. And then if they're below a certain threshold but above another threshold, they go through a proposal review tool where an end user says yes or no to individual proposals to whether or not they get accepted or rejected. We're doing something similar at Arizona DOT also, where we're facilitating the data roll-up of the county local road data in order for them to support the All Roads network, or the Arnold network. So Arizona DOT has a web portal where the data providers are submitting data up. That goes through the One Integrate engine to validate the data, and then it does the change detection, and then they take those changes and they feed those changes back to their source database. And then lastly, for those of you that are not necessarily GIS focused, we also do work in the CAD and the asset management validation arena. So for Google, we're validating their CAD drawings that are coming back from their engineers to make sure that the CAD data is of a certain quality in order to be fed into their asset management systems. And then lastly, we're also validating their asset management systems also. So these are non-spatial tables that are very convoluted, and running validation rules to make sure that the assets are valid and correct based off of their specific needs. So how do we enforce data governance? Well, we can do this through validation. So the first demonstration we're going to show you is how we could take data governance policies and build rules in a way to validate the data sources of those different policies. So for example, you may say you may set a data governance policy that my row data must be routable. So what do the actual rules, or what quality checks do you want to check to make sure the row data is routable? Or you might say the routes must support an LRS. So what does that actually mean? So we can write rules to make sure that the data would actually support your LRS. And then also maybe we also set some sort of policy about the way that row geometries are aligning to municipality boundaries. So we can write some rules along that. So with that, let's go ahead and flip over to the first demonstration. So in my map here, I have some data, and this is from data from in the state of New York. We have some township boundaries. So here's my municipality boundaries, and I have some street segment data. And what I have is I have some validation rules that I'm going to run against this source data. So let's go ahead and fire this off. So basically what we're going to do is in my map extent, I'm going to grab all the features here. So there's some 21,000 features, and I'm going to extract it into our One Integrate engine where we're going to run some validation checks against it. So we're going to validate 21,000 features, and here I have about 20 validation checks. So we're going to do somewhere in the order of 400,000 validation checks. And don't worry, it's only going to take about a minute and a half. And once we get those results, it's going to tell us where the issues are at. So the reason we can do so many validation checks and do them also in a performant way without running into memory issues is that we actually operate under an object-oriented disk cache. So it indexes the geometries and the attributions of each feature or each record in a way that enables us to do quick validation checks at the feature level. So this is the reason why we can validate very large data sets in an extremely quick manner. And this is why a lot of these national mapping agencies and state DOTs are using our software, because they have a lot of data. They want to be able to validate that data in a performant way so that they can make decisions off that data. So the first thing we're going to do is we're going to do my essential geometry checks. It's actually already finished these checks. And these check for typical geometric issues that we find in all GIS data. We want to run these checks before we even start thinking about other validations, because these can cause issues with your data sets downstream. So making sure you don't have duplicate features, making sure you don't have kickbacks, spikes, issues, geometric issues with the data that get introduced when you're doing geospatial editing. But then we want to do some other validation checks based off of those data governance policies that I mentioned before. So making sure, if we want a routable network, we want to make sure that there is a row name. And when I say a routable network, this can be confusing because different people have different definitions of what routable means, which is also a good reason to build rules to identify what you actually mean by a routable network. So if you want it to be fed into a navigation system, you must have a row name. Now, for the most part, most state DOTs don't necessarily want to feed their row network into a routable system. It's more meant for some sort of LRS-based system. So this may not necessarily be a validation check that you're going to do, but it's something that if you want a true routable network and navigation, you would need. We want to make sure that our roads aren't overlapping other roads. We want to make sure a road is not contained in another road. We want to look for overshoots, undershoots. So if we don't have proper connectivity, we can't do proper analytics against the data, whether or not it's routable in the sense of navigation software or routable and just trying to do route network analysis. This is another example of routable network. You want to make sure your roads are intersecting at the start and the end. So it's actually split at each individual intersection. As I said before, this may not necessarily be a check that you would do at a state DOT, but if you are working with 911 data, this is something that you would definitely want to have. And then lastly, for those of you that are state DOTs, a bifurcation check is something that is that we're already doing for a variety of different state DOTs like Kansas and Arizona, where you have a street segment that forks at the road. They have the same route ID, so you don't know where along the route the LRS is supposed to go. So identifying where these are occurring and then updating your route IDs based off of that could be important. And then lastly, we're doing some validation checks across different data sets. So making sure my streets are contained within a township. If they're contained in a township, they have the correct township left-right name. And if they share the edge, the left and right is attributed correctly also. So we're going to, when this finishes, which it just did, we can report on how well the data conforms to those individual rules. And we're pinpointing on the map where those issues are occurring. So if we take a look at this example here, we're pinpointing that we have a spike. But notice that we're pinpointing exactly where that spike is occurring. The reason why this is important is that there's a lot of other validation software out there that can tell you that there's an issue with your feature, but it won't tell you where the issue is occurring. Now notice the scale on that. I'm at a 1 to 2 scale. Imagine you have a route that goes from one end of the state to the other end of the state, and you have a kink in your network, and you have to zoom into a 1 to 2 scale and pan across 300 miles of road in order to find this location. That could take hours. So being able to know quickly where this issue is at, drive the user to it, fix it, and move on is very beneficial to a lot of our state transportation organizations. Here's an example where we have an overshoot. Notice here we have, it's kind of hard to see, but we can see that here's our overshoot, where we're validating the postal code. In this case here, my left postal code is null, which is outside that range of values that's acceptable. We're saying that it should be some value between 500 and 15,000. And then we have where my street is crossing over my township boundary, so it's not conforming because it's not contained inside the township. And then lastly, when it's contained inside the township, it must be attributed correctly. So if I take a look at this street segment, it's fully contained inside of Rochester, but if I look here, the street segment is attributed incorrectly. One is Brighton and one is Rochester. Oops. Not only can we do the validation, but we can also automate the cleanup. So if you define what does it mean to be clean and how do I clean it, we can automate that process. So for example, I can automate the process of cleaning up some of those geometric errors. So just like we had the essential geometry checks, we have essential geometry fix-ups that remove duplicate features, smooth out those kickbacks and spikes. And then we also have fix-ups to align features. So if you can define what does it mean to align my features and how do I want to align them, and it can automate that process of doing the alignment. And then we can also update attribution based off of the spatial relationships. So if the street center line is fully contained in a township, update that left-right township so it's attributed correctly. So let's take a quick look at the results. Notice how we removed that spike. Where we had that overshoot, it's now aligned. Where the street was crossing over, notice now it's actually aligned. And then over here, where we had that street segment, we updated the left, right, city, town name so that now they're both Rochester. Now, let's take a quick look at what these rules actually look like. So basically what we do is we connect to the data sources. This could be connecting to your enterprise databases. It could be connecting to CAD drawings, non-spatial or LRS-based systems. In this case, we're connecting to what's in the map document itself. And it brings in all the different tables and all the different attributes that are associated with those tables. So in this case, I could say my street name must not be equal to null. Or we can change this to say maybe it should be not equal to an empty string. Or in the cases of some of the validation checks that we did at Kansas, we were validating that the route ID was correct. So in order to check that, we were actually looking at a combination of fields. So we would say, in this case, I don't have a route ID field, but in this case, I would say the street name must be equal to the combination of multiple different field values. So we could come in here and we could choose what combination of fields it should be equal to, but maybe there's actually some sort of delimiter, whether it's a space or some sort of dash, so we can be as specific as we need to be in order to validate that the data is correct. Here's another example of a validation check that we're doing. In this case, we're taking the left postal code and we're making sure the left postal code is some value between 500 and 15,000. And we're doing the same with the right postal code, making sure the right postal code is between 500 and 15,000. But what we find is postal codes are stored as strings. So what we can do is we could take that string value, convert it to an integer, and then do that check. And what we're doing is we're doing this on the fly as we call a built-in function. So we're not doing it in the database itself. We're just doing this in the rule to do the validation check. And we have a whole host of different types of built-in functions, things to convert between different data types. We have geometric functions. So if you want to get the start or the end of a line segment or a road segment, if you want to intersect two different segments together and get the resulting intersection, a whole host of different geometric types of functions. Mathematical functions, and then we also have measure functions. So this is very important in the transportation world. Say, for example, you have some sort of project management database where it's built in an LRS, and you want to determine, do I have two projects that are happening in the same location or close to each other within a certain time period? Well, what we can do is we can build a line segment from the measured values and then compare projects to see if there's any projects that are in a similar location. And then lastly, we have some string functions. So this is what we do at the US Census for doing street name comparisons. We have functions to determine how similar two strings are to each other. So making sure that if somebody mistypes something, we could still find a match between those two. And that's using something like the Jera-Winkler similarity, the Levenshtein distance model, and the Soundex model. Couple other checks we have here. We're making sure my street segments, for all my street segments, there's 0 townships where the street segment crosses over a township boundary. And then we're saying if a street segment is contained within the township boundary, the left city town name and the right city town name are all equal to the township name. All right. So back to my slides. So this is when we're just trying to validate one individual data source. But what happens when we want to do some sort of data roll-up effort? We want to collect data from one entity or one data provider and roll it up to another. We find this paradigm a lot at every single level of government. We find it, the counties are collecting data from the local municipalities. The states are collecting data from the counties, like what Arizona was doing. And at the state level, the state is collecting data from at the country level, the country is collecting data from all the different states, like the US Census and like US DOT. Now, what happens a lot of times is these local entities, and in this case, let's just talk more specifically about state to local. The states are maintaining the data using some sort of schema that's meant to do whatever they're doing. In most cases, it's meant to be used as some sort of LRS-based system. The locals are using their data for feeding some sort of some sort of 911-based system. So because they're editing these data sets for different purposes, they're going to maintain the data in a different schema. Most definitely, they're going to maintain the data using a different representation. At the local level, they're going to have a street segment data set segmented at every single intersection or every time the road name changes. At the state level, they're going to manage the data as a route data set. So it's going to be one segment across the entire state. And then also likely the way that intersections are modeled could be different too. A lot of locals are feeding their data into computer-aided dispatch systems. And as part of that, they have to create what we call pinch points. So how do we take all this into consideration when we're trying to do the data roll? We can't just use your typical versioning in order to determine what's changed and what's different. We have to use a rules-based approach to define what does it mean to have two different data sets, how different are they, and does that actually warrant some sort of change in the system itself. So let's go show you an example of this particular use case. So here I have two different data sets. I have a state data set, which is my route data set. Notice here we have a route that starts here and goes all the way down to this location. But if I look at the county data set, we could see that it is segmented all along here, right? So when we're doing the change detection, we don't want to just say, well, if it's segmented, it's different. The state is not necessarily caring about that. And we're also, if there are slight differences between the way that it's digitized, the state may not care. In some cases, we find that the state data is more accurate than the county data because maybe they've gone out and done they surveyed the locations. So they don't want to update any sort of changes that are slightly different. So we have to build tolerances to determine what's different and how different it is. So with that, we're going to flip over to OneIntegrate. Now you're going to notice I just changed interfaces on you. This is the OneIntegrate Enterprise Edition. And the reason we're going to be using the OneIntegrate Enterprise Edition is that we want to start connecting into more different data sources. So in this case, I'm connecting to my data set and I want to do my change detection. So I'm going to fire this off and then I'll explain what we're actually doing here. So we're connecting to the county data and we're connecting to the state data, and we're going to do a set of change detections. And this is all happening in what we call our session. And the session consists of open data tasks that are connected to data stores, and then a series of rules and actions. So for example, if I select this particular open data task, you can see here we're flipping to my data store. We choose which data set we want to connect to. So for example, we may want to connect to some sort of Esri-based GIS database, but we don't have to. We could connect to CAD drawings. We could connect to non-spatial databases like an Oracle database or a SQL Server database, or maybe we want to connect to the native spatial types for those different databases. So we could choose which data sources we want to connect to, and we're not limited to just one. We can connect to multiple sources, which I'll show you an example of in a few minutes. So when we connect to this data source, it's going to read in the schema. So it's going to know which tables are available and what the different attributes are or the different fields are for that particular table. And this way we can write our rules against that schema. Now, in some cases, the data may be slightly different than the way our rules are implemented. So in that case, we can actually do some schema mapping in the interface itself to make the rule authoring process a little bit smoother. Rules are where we define what the data should conform to, and actions are what we do when something doesn't conform to that rule. Do we report on where the issue is occurring, or do we do some sort of fix-up, or do we do some sort of change detection? So in this case, we finished running that change detection, and we can take a look at the results. So in my map here, I have my proposal data set that we're going to overlay. And basically, it's identifying where we have changes between the data sets. So if we go and zoom into one of these areas here, here's where we're identifying that there's an add. Now notice how you have the state data set, and then you have the county data set. This has been added, so that's why it's being flagged as an add. But notice that we're not flagging any of these issues, even though they slightly are off. That's because we are using a tolerance. In this case, I think we're using a 15-foot tolerance. And we're saying that anything within a 15-foot tolerance, what percentage of the road center line is contained inside the other, and then what are the bearings of the data set. And if those are all within a certain tolerance level that is configurable, we determine whether or not it's a match or not. So we can now, once we have all these proposals, we then can determine how we want to integrate these into our data source. So that's an example of an add. Here's an example of a delete. So it is in the state data set, but not in the county data set. And this one's an interesting one here. This is where we have what we call a reshape and an add. So what happened here is here was the original data set for the state. The county data set they created a new road, and then they connected the old road over to connect to this particular road. So in that case, we have an add, and then we have a reshape because this geometry has been reshaped to align to this new road. Now, where it gets a little more complicated is we start getting into the way that organizations are managing their intersections. So sometimes we start to see these corner cases where all of a sudden we're getting false positives. So there's a couple ways we can handle these false positives. One, we have this proposal. We could give it a low weighted score because maybe the bearings are slightly off, but the geometries are actually within a certain tolerance. So it might have a certain weight. So we could drive the user to it and they can accept or reject these issues. Or when we know that something occurs a lot, we can handle it inside the rules engine itself. So for Kansas, when we identify where we find these types of pinch points, we have a rule to identify that. Oh, that's interesting. Oh, that's the buffer. That's why. We have a rule to identify that where the pinch point is and what type of pinch point it is. But then what we can do is we can say, well, maybe what we want to do is we want to, on the fly, let's update the way this intersection is being represented in the county drawing so that it's more similar to the way the state is representing the data. In this case, we create something like this. Now, what we're not going to do is we're not going to take this result and send it back to the county because the county needs to maintain their data in the way that their intersections are maintained in order to facilitate their 911 efforts. So what we want to do is we want to only find out what's different between what was submitted last time and what was submitted this time. So we can use this newly updated on-the-fly data set to determine whether or not we have matches or not. So notice now we flipped to a updated proposal data set using where we use the updated centerline data set, and now we're getting matches. And we could do this across. Here's another example here of another example where we had the pinch point, we've updated it, and then we run the change detection, and now we are getting a reshape over here, but we're finding matches here. And then we have some pretty crazy intersections. Here's another example of an intersection where the original one had all these false positives. On the fly, we've updated the intersection, so now we're not getting those false positives anymore. All right, so now we're starting to get into, so we've talked about GIS to GIS. What about LRS to GIS? So doing some sort of interoperability between your non-spatial systems and your GIS systems. We find that you may have asset systems or project management systems that are LRS based, where there's no geometries associated with each individual record, but you do have a route ID and then you have a begin and end LRS value. And then you may have a GIS system that is encoded with measure values. So what we can do is we can connect to both of these systems and determine, does that asset actually exist within the GIS? And if it exists inside the GIS, or if it doesn't exist in the GIS, let's flag it. Or is there a missing asset in the LRS based off of the geometric network? And we've done this for working in like pavement systems and project management systems. And we've also done a lot of work of this in HPMS. So I mentioned in the beginning where we were doing these validation checks for HPMS for federal highways. And as part of that, the HPMS data is stored in an LRS. And what we need to do is we need to map it to the GIS in order to do these geospatial analysis against the data. So geospatial validation checks as opposed to just attribution validation checks. So let's show this particular example. Here I have a statewide data set, and what I want to be able to do is I want to take all the event data or all the data items that are in the LRS and map them on to the network in order to do my validation checks. So let's go ahead and flip over to OneIntegrate again. So in this case, I'm going to connect to multiple sources of data that are not, one of them is all non-spatial data sets. So this is where we have my HPMS data items, so AADT and so forth. And then I'm also connecting to my route. These can be in separate databases. They can be in separate systems. As long as the OneIntegrate product can connect to them, it can bring them in to do the validation checks. Once we bring these data items in, we can we can build out my event data set. So this is an example of building out the event data set so that we're leveraging the measured values. So we're looping through all the data items and we're finding the route where the route IDs are the same and they're within the measured values. We can build out a dynamically segmented data set. So in this case, we're writing them out to the sections table. Once we have that information, we can then run the validation checks. Now, I'm not going to run this live. This is for an entire state running HPMS validation checks. This could take 5 to 10 hours. So we're not going to run this live, but what I'll do is I'll show you the results. So in my map here, we have, let's go ahead and zoom to what we're actually doing here. So I have my route data. So this route data starts here, goes all the way over to here. It has some measured values. So if I look at the geometries, we'll notice we have X, Y, and M. And what we want to do is we want to take the LRS table and segment the data based off the LRS table. So we create something where we have an event or data items along this particular network. Then once we have this information, we then can start to run validation checks on that network. And one of the things we want to do is we want to determine, are there any places where we have overlapping or are we double reporting anywhere? So for example, here's an example where we have routes that are overlapping. We're flagging which route is overlapping. And if I select this particular item, we're going to see that we have 2 routes that are overlapping. Now, one is a eastbound route and one is a westbound route. So this could be a valid situation. So I think what we would do from here is we would sit down with the organization, the transportation organization, and we would say, well, is this something that's valid that can happen? And if it's so, we can update the rule to say, well, if there's an overlap, if one's eastbound and one's westbound, that's okay. But likely, you may want to actually represent this as some sort of dual carriageway instead. So that will need to be handled. But we also want to be able to do is not just find where we have overlaps, but where do we have gaps? Where are we not reporting on a particular item that we should be reporting on? So for example, especially when you have like a full coverage data item. But in this case here, we have AADT and we seem to be missing or not reporting on AADT at this section of the line. So what we can do is we can identify where these are occurring. And a lot of times this is occurring either at the start or the end of the line segments. So identifying where these are occurring. We've also found in some cases, some organizations say that they have what they call data shrapnel, where they, in their GIS system, they've updated the data set, and for some reason, something didn't fire off behind the scenes of that GIS, and it's creating little slivers inside of their data sets. So we can also use these same rules to identify where those are occurring. We can also do the validation checks on the attribution of the data sets. So this can either be done on the table level, or this can be done at the GIS level. So in this case, we waited till we converted it over to GIS to do that check, but it could have been done at the non-spatial level. So in this case, it's saying that we failed the domain check for AADT. If I look at my AADT item, I could see here that the value is null, which is why it's outside that range of values. And then lastly here, this is where we're doing my coverage check. And let's go ahead and flip this over here. Okay. So in this case, this is where we're doing more of a spatial or topological validation check. We're saying that if there's a facility type and there's an NHS or National Highway System line or event, there must be an AADT. And what we can see here is that we're missing an AADT at this particular location. So we flag that as an issue. So it's missing it. And we're using the topology in order to do those checks. So what we're finding is that not only are we're doing this at the federal level for federal highways, we're also finding states are interested in being able to do these validation checks on their source data set. So not necessarily having to send that data up to federal highways to get those results. So if they can run it as close to their source data as possible, they're finding increasing value in being able to identify that and using the same rules that federal highways is using, but running it locally in their environments. So that was an example of an LRS to GIS. Now we have some other examples of where you can go from CAD to GIS. So just like we can connect to non-spatial systems, we can also connect to CAD-based systems. Now there's a lot of issues when you're trying to connect to a CAD-based system. Your CAD drawings are a lot of times in paper space and not in GIS. If you're lucky, you may get 2 reference points for where they're located in GIS. But unfortunately, a lot of times that they may be accurate in those 2 locations, but it's distorted everywhere else. So your CAD data is not going to align to your GIS. And then a lot of times your CAD drawings are a schematic representation, and not a real world representation. But what we can do is we can connect to those CAD drawings, validate the CAD drawings and make sure that they're meeting a specific standard that we set up. If they meet that particular standard, we then can integrate that into the GIS using that same rules-based approach. And we've done this with intersection data, so having intersections that are CAD drawings and migrating that into the GIS. And we've done this in the utility space, so taking a electrical utility manholes and identifying where they're located in the GIS, all through an automated fashion, and integrating it into the GIS and aligning the wiring all correctly. Now, I don't have time today to go through the demonstration of this, but this is something that you are interested in. We could definitely go over this at a later time. Another use case, I'm running out of time too. Another use case is dealing with taking fatality accident report data and associating it onto the Arnold Road network it exists. The main use case for this was that the USDOT wants to validate that the fatality accident reports are actually being attributed, or validate that the attribution in those reports match what HPMS is saying that is occurring there. So as part of that effort, we had to first take road names and conflate road names over to the Arnold network, because if we wanted to determine where the farthest point was, which road it was connected to, we can't just use a spatial relationship. We want to use attribution. So we did that conflation of the road names. We've actually done this for a lot of different state agencies where we've conflated over attributes onto their network. So we can either do that by doing a straight conflation by just taking the road name and putting it onto their network, or we can create events along their route based off of that information. But anyway, so once we did that, we then can identify where that farthest point is associated along the route network, pull the LRS information, and then we could do that cross-feature validation check. But as I said, we're running out of time, so I'm not going to do a demonstration of this today. But if this is something of interest, we can definitely cover this at a later date. The last example that I wanted to cover is something that we've done. This is a utility example, but I think all you transportation agency organizations can understand the relation to how this relates to transportation. So when a utility company in the UK needs to do any sort of construction, where they need to do a dig on a particular road, they got to submit their plans in order to facilitate that the work that they're going to do is safe for the employees, but also making sure that they're going to keep traffic flowing as smoothly as possible. So this goes through a review process, and there are some very convoluted manuals in order to determine where things need to be set up. And then once you determine where those need to be set up, you submit this to a entity that approves or rejects your plan. So being able to automate this process is very interesting to a lot of organizations. So basically what we did for a particular gas organization is we took the traffic signs manual, which defines where traffic signs need to be put up when you're doing construction, and how to build a safety street works and roadworks location, combine those together and build rules to determine when you do a dig, what does the layout need to be, and automate that process so it makes it a lot easier for these gas companies to, when they dig, to automate the process of building out where they're going to dig, what their work area is going to be, what the safety zone needs to be, and what signage they need, so that it makes it more smoother to approve this process. So basically the way this works is they first need to be able to, because they need information about speed limit information and traffic flow in order to automate this process based off the rules in those plans. So the first thing they do is they conflate over the traffic information from the Ordnance Survey highway data set over to their road data set that that particular energy company is maintaining. This will be very similar to how maybe pulling information from HPMS onto a local road data set that an organization may have. So then what they do is they go in, they using a tool, they digitize where their location of their dig is going to be. Then the rules kick in where it automates the process of creating the workspace. So it's big enough to fit where they're going to dig all the equipment they need and their van. And then what they're going to do is they're going to create a safety zone with the lead-in taper and creating a buffered area to make sure that the area is safe. And this is all dependent on the width of the road, the speed, and the traffic flow information. And all of that is defined in those manuals themselves. And then lastly, we're going to create the signage and determine what kind of equipment we need. So I don't have access to this machine, this application directly, but we have a video that can demonstrate what's happening in this particular application. So basically what we're going to do, and I'm going to skip ahead a little bit too as we're going through this to make sure that we leave some time for questions. But basically what's going on is the user puts in an address or a location where they're going to do a dig. They're going to draw in the area that they're doing the particular dig location. And then once they draw that particular area, it's going to automate the process of building out the work area that's needed for the equipment that they need to do that particular job. And then it's going to build the safety zone area. And then it's going to put in all the signage. And what I'm going to do is I'm going to skip ahead. And let me explain also what technology we're using here. So what you're seeing here, the interface itself is leveraging GeoCortex by Latitude and Esri technology in order to facilitate the editing and the creation and the visualization of the data. But then we're leveraging the One Integrate Rules engine to automate the process of building out where the work area is going to be and where the signage needs to be based off of rules-based approach. So we're running the analysis. This takes about a minute to run. So let's go ahead and skip ahead. And then once we run that, we're going to then display in the map itself where the work zone starts, what type of equipment is needed, how spaced these cones need to be, so that you know the number of cones you need, where all the signage is going to go. But then what we are also going to be able to do is we're also going to be able to take these results and build a report that needs to be submitted to the actual approver. So we can go in here, we can create a report. I'm going to skip ahead a little bit. And then we generate the report so that this can go and get approved. But as part of this report, we also know what equipment we need, so we can create a checklist so that when we are sending people out to the field, they know what equipment is going to be needed. And then lastly, they also need to send out a mailer information to mail out to all the people that are going to be affected, because this is part of the policy. So what we can do is we can also, leveraging the information, we can build out who needs to go where, who needs to get letters to tell them that there's going to be construction in their area. All right, so with that, just to wrap up, in order for you to have proper data governance, data quality is a huge aspect of that. And knowing what the current state of your data is at and where you want to go is part of generating that data governance plan. So you want to make sure that when you build out these business requirements inside of your data governance plans, there's a way to make sure that there's a quantitative quality metric piece of it, and identifying what type of rules will be required in order to meet those data governance plans. And this is a feedback loop. So as you come through and you develop these rules and you see what the results are, this can feed updates to your data governance plan. So with that, I'm happy to answer any questions that anyone may have.
Hi, so Kevin, this is Sheila.
All right.
And there's a few that have come through. So the first one, I know we're short on time, but I'll try to put them into a little bit of a synopsis. So the first one is, it's kind of a combined question, is there a limit to the quantity of data that can be validated, and or is there a limit to the number of different databases that you can validate against?
No, so No, as in there's no limit. The limit is, I mean, based off we leverage an object-oriented disk cache in order to do the validation checks. So as long as the data the hard drive is big enough for the size of the data, it can be ingested into the engine itself. So there's really not a limit, and the way that it indexes the features, it enables us to handle national level databases extremely quickly and in a performant way. So, for example, we've done validations across an entire network across the US and not ran into the memory issues that you would run into if you were trying to do that into some other base system.
All right, and then the next one is, do you have to automate the fix-ups? And there were a couple of these. What if you don't want the system to automatically apply the fix-ups? How can you review them before accepting them?
Oh, okay, yeah. So in the that's kind of like the U.S. Census use case. So at the U.S. Census, what they do is, and other organizations do, is that instead of automating the entire process of feeding everything directly into the database, it builds what we call proposals. And those proposals have a confidence score associated with each individual proposal so that there can be some filtering out so that you only focus in on proposals that are within a specific range of values. And those go through some sort of reviewing process. So there'll be a tool where they literally say yes or no based off of whether or not the change is a true change or whether or not it's some sort of false positive. So being able to quickly accept and reject. Once it goes through that process, then at that point, since they've been approved, only the approved ones go back into the source database.
Okay, and then the next one is, can you do conflation on either attribution or spatial features using commercial data sets?
Okay. Good question. So you can do either, and I know I didn't have I was trying to cover a lot in a very short amount of time, so we really didn't focus too much on the conflation aspect. So there's some cases where we've taken attribution from one data set and mapped it over to another data set. So pooling, like for example, maybe it's like here data or TomTom data, pulling out those IDs for the here IDs onto the network itself so that they can get the traffic information on their own network. But then vice versa, we've also worked with organizations where they want to take their network and realign it to another network that may be more spatially accurate. Sometimes this is taking county data and aligning it to the DOT data, or this may be taking a data set, maybe even at the county level, and aligning it to a third-party data source like here data. So doing attribution or geometric conflation.
Okay, cool. And then the last one is around the rules themselves and wanting to know, can the user share the rules, or is there a place where you can find rules that may have already been developed, like the example of the HPMS rules?
Oh, good question. Okay, so for our existing customers, we have a portal that allows them to log in and converse with other customers where they can pose questions. And in that location, we can, it's not just the customers, but also the OneSpatial staff also responds and stuff like that. But then also as part of that, there are rule sets that are specific to like the transportation group, where we have a GitHub site where you can download those rules and deploy them inside of your OneIntegrate technology. And that's a place that people can share rules also.
And it's easy also to sort of package them up right directly within the OneIntegrate product.
Oh yes, yes. So they have you can select which rules or which rule sets or however you want, or basically any single different data item inside the interface itself. You can download it and then restore it in a different application. So if you want to share between two different states, you can literally just select which rule set, say download it, and then go give that to your friend across the street at another state DOT, and they can just upload it to their application and deploy the rules there.
Okay, great. I think there were some that were sort of duplicated, so I think I got to the primary ones, but we're about out of time now. So if there is the communications us1spatial.com email up there. So if anybody has any questions, also a lot of you probably have our emails as well. And so, feel free to reach back out, and we'll be happy to answer anything we may have missed, or actually set up a one-on-one session
All
with
right.
anybody
Thank you.
who's interested.
Yep. Thank you, everybody. You have a good day.
Thanks.